Hi again, everyone. Thank you so much to the organizers for having me, and thanks everyone for joining. I am excited to discuss some exciting machine learning physics overlap with you. Give me 1 sec to start sharing my slides. There we go. Okay, so from your applications, we noticed that you have very different varying backgrounds. So lots of you already know so lots about machine learning, and some of you came here just to learn from scratch. And I have a first lecture. So I think I am going to go with explaining very basic concepts, but hopefully combining them with some intuition that will be useful also for those of you who are already familiar with these kinds of topics. And yeah, I am going to try to interact with you a little bit so you don't fall asleep. So for those of you who are watching on Zoom, if you have a question that comes up during like non-question time, just write urgent with your question in chat and I will answer. And for those of you here, just raise your hand. Just raise your hand anytime. So first thing, maybe let me ask you a question. So we are here because machine learning happened to be very productive tool that people have been starting using like across different fields and more recently in physics as well. And so I am curious if you already know what it is. Does anyone want to tell me what's machine learning? I see a raised hand over there. Do we have a microphone? Yeah, you have to for the recording purposes. Yeah.
So I would say that it's an automatized process to extract knowledge and information from data, learning from data, basically.
Mm-hmm. So would you also know, that's just a non-committal follow-up question. This was great. Would you also know what's then difference between like, if I would say a standard algorithms, like before machine learning algorithms, what's the key difference?
That standard algorithms are probably easier to explore and interpret, while machine learning, especially when it comes to deep neural networks, is a bit more hard to interpret and to know what's going on, basically. It's more of a black box tool somehow.
Okay, great. Anyone else has a follow-up on this? I see raised hand back there. Thank you so much, Anya.
Yeah, I think a machine learning algorithm is, compared to a normal algorithm, performs better by a performance measure on a task with amount of data, with amount of experience, while a standard task always will perform the same.
Mm-hmm. Okay, this was a great start. So you already told me the super key things, that machine learning algorithm, the algorithm adjusts itself as it learns on the input. It's not that I know upfront a set of for loops that I can write. The typical example of this would be, as you for sure already heard, if I want to distinguish between a dog and cat, I can go into the insane length of writing an algorithm that will describe all the qualities and quantities that a cat could have and try to formalize it. Or I can just show, let's say, neural network, a lot of pictures of dogs and cats and let it to figure out what the difference is such that it can classify the further pictures. So you might have heard about different subcategories about supervised, unsupervised, and reinforcement learning. I mainly here want to say that these are not super separated classes as they might seem. That is all blurred boundaries between them. And once you learn one, it's not so hard to transfer to the other. So it's super important that you understand the basic principle and don't worry about like that reinforcement learning maybe is hard. I don't understand it. So yeah, so these connections behind, they are not like actually real. This is just like something that I found in this interesting archive paper about word cloud generation. But okay, so this was just a quick thing, and you told me correctly that machine learning algorithm learns general rules from data. So now I have the next question for you. With these dogs and cats and big data that we have now available in many different non-quantum applications, we understand how it works. So how about quantum physics? Do we have some big data in quantum physics? Does it make sense for us as a physicist to extract rules from data? Isn't that contradictory to how physics is built on a toy models and stuff? Anyone wants to weigh in on this? I see here in front.
Yeah, in some fields they have very big data, like in particle physics, astrophysics. So it's not always maybe toy models that were used.
That's great. But this school is specifically about quantum physics and chemistry. But this was an excellent point. There are fields of physics where big data comes naturally. What about the quantum stuff? Any ideas? I see a hand over there.
In some field of quantum physics, we actually know more information than we usually do in cats and dogs classification. For example, we know anormalized distribution, Boltzmann distributions, and other information that we can use to implement our machine learning algorithms.
Interesting, interesting. Anyone else has an opinion or where the data would come from for a quantum physicist? Please.
Okay, so I wouldn't have said anything about where the data comes from, but just that it is like one more tool that you can use if the classical approach of having a toy model doesn't work, or maybe you could just try out if the other tool with machine learning works better.
That's great. We have another raised hand. Please go ahead.
I would say, I mean, could come from simulation or from experimental data, some quantum devices, which we could then model the model.
Okay, this is great. Thanks, everyone. So this was an excellent start. So we actually do have big data in quantum physics. And there is one object that you work with all the time that actually does not scale all that well when you think about it. There are examples that you solve in your quantum mechanics class, like a harmonic oscillator that you can solve analytically. So it doesn't so much matter. But for a lot of problems in physics, we don't have analytical solution. And when we are solving problems numerically, the size of the wave function, the central object that lives in your Hilbert space, blah, 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 that you know everything about, does not scale all that well. If I have two spins, I will have a Hilbert space size 4. When I have 10 spins, I will have over 1,000. And when I have 100, I will have like 10 to the 30 if I want to solve the problem exactly. Anyone wants to tell us why this is? I'm sure you know this. And if you don't know for sure, just don't worry. Just get us started with some thoughts. We have a hand over there.
I would say it's about the exponential growth of the Hilbert space and the number of configurations the wave function can take.
Yeah, that's correct, right? So if you have a classical state of two possible states, you will have one configuration and second configuration. In the Hilbert space, you can have any superposition. And when I start to generalize this logic to n spins, for n spins, each of them I will just describe either it's in one or it's in the other, right? So that's n numbers. But for for n quantum objects, I am going to start creating these superpositions. And every time my Hilbert space grows by extra multiplication into this long superposition, every time I add a spin, right? So I end up actually with 2 to the n numbers describing a wave function. Is this clear? Everyone understands this. That's super important. And this is where these huge numbers comes from. And this is why people tell you that we need quantum computers or we need some super smart, effective, approximative numerical techniques, because these numbers become very quickly super big. I always put as a joke, this people say that age of the universe is 10 to the 22 seconds. It doesn't tell me much about the length of the vector, but it sounds like it's a big number, right? So probably it's bad that if I want to describe 100 spins exactly, I need 10 to the 30 numbers. So you may know that now we can classically simulate, I don't know, around 20 to 50 spins, depending what kind of strength cluster do you have. But actually 50 is a bit of an upper bound. But so this is the thing, that the wave function itself that you work with in quantum mechanics on a daily basis actually does not scale that well. And now there is a second thing, and that's also something that you guys already mentioned to me. So you know that wave function is this thing that lives in the Hilbert space, but there is a second kind of disconnected thing, and that's experimental measurements. I cannot go and measure a complex wave function, right? So we measure projections or a weak measurements, but we actually get the experimental readout that is some kind of projection that compresses, that gives us some information about the wave function, but the single measurement doesn't give us much. So this is kind of how this distinction between toy model driven physics and data driven physics also comes in place. If I am a theorist and I start on the right hand side here, I will write some toy model, Hamiltonian, and then by diagonalizing, I find the wave function, and from that I can predict all the different topological order, what's probability of getting different measurements, and so on. And already this scales badly, and we complain about it often enough. But then there is the second problem, that from the experiment, I need to measure a lot of experimental real data to reconstruct these things. And that reconstruction actually doesn't scale all that well either, right? So when someone asks you if we have a big data in quantum physics, you can answer yes, of course. And then there are two things. And I need to admit that I'm a little bit coining the term of quantum big data here, because this means the fact that the wave functions scale badly, it means something else than astronomers measuring 60 terabytes of data, right? It just means that like your central objects to your theory actually do not scale great if you want to simulate them numerically. And then there is second thing, that as a quantum experiment, especially as a quantum experiments are growing in space in size, you are actually dealing with the same-ish type of large-scale data as astronomers, because you need to collect tons and tons of it to verify your quantum simulator or understand what kind of quantum computation your quantum processor is doing, and so on. So somehow now we are living in a really cool time for a condensed matter physics, because there is this beautiful intersection between these toy models and data-driven approaches. We are developing new numerical techniques to solve some of this like intriguing and complex toy models on left-hand side all the time. And at the same time, condensed matter and quantum technology are now in the scale that you can straightforwardly test them in the lab. So you have both sources of data, as someone mentioned here, both numerical and experimental. And then indeed you can ask yourself a question: can I extract some physics from these data? Can I understand something more about if my toy model estimation about my system were correct? Can I understand something more about what kind of physics is happening? And can I maybe even find out something that my initial assumptions when I was modeling the systems have missed? So last part of the sort of introduction I want to give you. So now you understand this very basic idea where the data in quantum physics come from. So let me maybe mention a few possible applications that are already in progress and people in the labs all around the world are using them daily. So this is kind of what I already hinted at, and this is very generic and challenging topic, and that's let's say you want to discover a new order of matter that you didn't know was there. Can you look at experimental data and guess something new is happening? So this is kind of this very data-driven physics discovery approach. And this is something I'm going to cover in this first 2 hours we have together, albeit on a very simple example. Second thing is an automated control of quantum devices. So this is different type of complexity that is also very funny. You might have seen a lot of pictures of experimentalists posing with their fridges or with their optical setups. And you see that there is going a lot of wires or lasers into such a system at all times. And actually what oftentimes happens is that these experiments, especially when you have a large number of qubits, a student has to sit there, typically PhD student like you are, 24/7, just turning the knobs to make sure that the qubit didn't escape somewhere. So if you actually want to perform quantum computation, and now people are investing and big companies are building their own quantum computer, maybe you don't want a PhD student to come in touch with that. So actually, this automated control is a big challenge. And again, it's something that machine learning can help with. And I hope towards the end of my part of this lecture series, I can show you some fun examples. Then there is a super cool thing that you can actually design both quantum experiments and new materials. There are very cool experiments going on where AI is designing your optical setup with the objective of producing a specific final state. And it's really cool that the AI could actually come up with some creative solution, even from the point of view of the experts. And then you can also design new materials, which I think you might hear about from Roman Krems in your quantum chemistry part of these lectures. Then there is the next thing in the sun. And that's what we just talked about as a good example of quantum states not scaling badly. Maybe you want to approximate them. I am sure you know a lot of numerical techniques that already do that. One thing that you can do is to just approximate the quantum state with a neural network and see if it's an efficient approximation that gives you a good prediction for the experiments. And there are very promising examples now where it seems that neural network actually in a specific cases outperform some of the previously known ansatses. And Giuseppe Carlo will tell you a lot about that. Another thing is this benchmarking of quantum computers. So think about it like this. We say that we want to build quantum computers so they could calculate all the things that all the combined computers on Earth cannot calculate, right? So that's great. So we built the first generation of quantum computers that potentially have enough qubits that they cannot be classically simulated. But now tell me this. If I have a first prototype of quantum computer that cannot be simulated in any way, shape, or form by a classical computer, that my PhD student built in a basement, how do I know that it's actually solving the biggest problems in quantum chemistry if I cannot verify what it's doing, right? So there are questions about benchmarking and verification and other things like error correction that are related to this. I will try to give you teeny tiny simple example how this benchmarking works, and Evert van Nieuwenburg will show you some more fancy error correction stuff. And the final example that I could come up with is discovery and optimization of quantum algorithms. You may also know that the question of like, what are we going to do with quantum computers when we have them is kind of open. I keep mentioning this quantum chemistry because that's very straightforward application, right? I know that I have a chemical, it's described by the wave function of all the electrons and protons and everything in it. But I also know from what we just discussed that that scales terribly. And even for the small chemical, I cannot write the exact wave function. But if I have a quantum computer, it's quantum. So the electrons are going to simulate themselves, roughly speaking. So I can handle such a problem, right? But apart that, finding an advanced algorithms that are doing optimizations or actually solving a really difficult pressing problems, that's a very much of an ongoing research. You might have learned in your quantum information class about Shor algorithm, for example, which is totally amazing achievement. But think about it. When you have a quantum computer, are you going to sit around and factor big numbers and be happy about it? Probably not, right? So you want to find some practical application. And this is again where AI and machine learning can help. And Florian Marquardt has some exciting work about using reinforcement learning for discovery of quantum algorithms. And I think he will tell you about that. Okay, that was the end of the introductory part. Are there any pressing questions right now? I don't see any. So from now on, I am going to assume that you all understand how wave function scales with the size of the system and why, and what are the different applications of machine learning and quantum physics. And you should have a first intuition why it makes sense to apply them. Now let's forget for a second about all of this and go back to physics. Raise a hand who has previously learned about an Icing model. Excellent. Everyone knows. Are people raising hands on Zoom? Out of 20. Okay, then I'm going to take it slowly. Okay, so you may already know that Icing model in two dimensions describes spins on a two-dimensional lattice where the two spins that are sitting next to each other on the lattice are coupled with a constant J. And this is how the Hamiltonian that gives you the energy of such a spin configuration looks like. You have for sure seen this before, right? So for example, this tells you that if sigma j, sigma I are aligned, meaning the product of them is +1, I get the energy minus j. And that's a lower energy than if they are misaligned, the product is -1. So this Hamiltonian gives me energy plus j, right? So this has a lower energy than this. Now you have a Boltzmann distribution that tells you how these different energy configuration are distributed at the temperature, at a given temperature. So basically what happens is that if I add the temperature, the difference between this and this is going to become less pronounced, right? And then you have some probability distribution for all the configuration given the temperature your system is at. Okay, now you all saw this before. So let's do quick icing quiz. Which of these configuration has the lowest energy? I wrote the Hamiltonian for you again in case you want to calculate it. I think either you have a remarkable physical intuition or maybe you want to calculate it. So let's take a few minutes and just go ahead and do that. So I see that a lot of people is not writing. So do we have some early guessers? We have a hand all the way up there. And then I will remember you in a red shirt after that.
I think A has the lowest energy because it has the most aligned pairs.
That's right. Do we agree? Exactly, right? So you can also, you can do.
It's not only the number of spin-ups. I mean, it's the boundary which counts.
Yes, yes, that's exactly right. So the number of unaligned pairs is minimal, right? But also you could just take this and just like calculate it pair by pair and figure it out. But what you just learned from this is that you don't have to, right? You look at it for a while and you can quickly see how to identify that it's the misalignment problem that is adding to your final energy. So you may also have heard that this model has a phase transition between the states that have some order in them, that are aligned, and between the states that what's up and what's down is completely random. And this phase transition is related to the temperature. Maybe you remember that you calculated it at some point in your statistical physics class. I don't remember the calculation because it was quite annoying, right? It's this Onsager solution. You have to do a lot, but basically what it boils down to is that you have to check the magnetization of the system and find a point where it turns to zero, where it is completely random. Okay, so let's say for the sake of argument that you are like me and you don't exactly remember how to solve this and find this critical temperature where the phase transition happened analytically. Also, I should say it's super special that you can find the critical temperature analytically, right? Like you may know that these phase transitions are famously a tricky issue. So now we reminded ourselves of how Icing model works. So then I am going to take a step into a different direction because we are combining two new fields here, and introduce you to something called principal component analysis, or a PCA. Who has already heard about this before? A lot of you did. Anyone wants to explain us quickly the central idea? So everyone has heard about it? No, perfect. Please.
So as far as I remember, the basic idea of a principal component analysis is that you have some data that has some features, as we have seen here. So this is in some space. And what you basically do is that you turn the axis of the data so that you get one axis with a very high variance of the data, and then you basically have axis with lower variance of the data, so that you basically know that you have like the most important direction of your data, and then in this way you can basically reduce the dimension of your data.
Mm-hmm. Very good, perfect. I saw other hands. Any of you has a quick follow-up, or you are happy with this explanation? I see that you're happy. No surprise, it was very good. It's exactly like that. Principal component analysis finds you a direction along which that sort of best follows the data in the minimal square distance sense. And then you can find the vector that follows the data the most, the vector that follows the data second most, and so on. But let's just take two for the sake of argument. Then you take these directions as your new axis and you transform the data into this new coordinate system. And ideally, you will see something cool. With these blobs that I randomly drew here, you don't see much. Now, let me show you something super exciting. This is what you are going to see when you run the PCA on the Icing configurations that I just showed you. You will get in your exercise notebook from me a lot of Monte Carlo samples of this Icing model. it's going to look exactly like this combinations, like this configurations I show you, except that you are going to have a lot of them. You organize them into the big matrix. I will tell you in a second exactly how to do it. Then you run this principal component analysis, meaning you find the direction that has the least standard deviation and the direction that has the second least in your data. And then you just project your data into this. And this is the idea that Lei Wang, who is also one of the lecturers at this school later in the week, had in 2016 already. And what you see in this plot is that you have two big clusters, right? There are these two. So what are the blue ones going to correspond to in terms of the spins? Anyone? Yeah, perfect. Just into the microphone, please.
The two ground state energies, all spins up and all spins down.
Perfect. And the middle one is then everything mixed. Okay, maybe how do I? Yeah, right. So maybe let me now explain you more like mathematically how it works. But if you cannot follow every formula, like don't worry about it super much. I will try to explain as clearly as possible, but it will get clunky. So it's mainly written here so you can do your exercise, but let's try to follow together. So you take your data and you construct a matrix. So each instance of your data will be a vector in a matrix. You put them column-wise and you have a matrix. Then you make each row to have a zero mean. That's just because so your coordinate system would be centered at zero. And then you find a vector W1 that minimizes this expression. So what is this? First, you project the data on your W1, then you take a mean, and then you normalize. So then that helps you, and then the W1 is your first principal component. And then you find all the next one by doing the same. So first you take your data and subtract the principal component that you already have a Gram-Schmidt style. And then you minimize, then you find a vector that minimizes the same expression. And you can continue like this, right? So in your exercise notebook 1, you will have Monte Carlo samples. For this, I also especially need to acknowledge a team from the t-Neighbour group from University of Zurich who was helping me prepare this stuff when we were teaching another course. So you will have these samples. So now there is a trick. They are two-dimensional, but we just said you have to combine everything into the one big matrix. So the trick you are going to do here that I'm already telling you in advance is that you are going to flatten this two-dimensional square into a vector that is just a column vector, right? And then you can put all the column vectors into next to each other and you will have a big matrix X. And all you have to do is to find these principal components. And in your notebook, it will guide you through how to do it with using a singular values. So now let's look at it. Let's look at it again. You can do this thing. Go through the solution, find the critical temperature. If I put the constants here equal to 1, I will get something like 2.27 for a critical temperature. Or let's say I wouldn't remember anything about this. And someone would just give me different Monte Carlo samples of my problem. Only thing I did is the clustering, which you will learn to hard code, but most of the software just has whatever .pca that you can just run. And you will get this thing. And you already told me by looking at it that you recognize that there are two phases, two clusters, one high temperature one and two low temperature ones, which is two possible ground states. Now, if I squint at this, a lot, and I will exactly check the color of these mid transition points and identify it here on the color axis. I will see that I am approximately halfway through between 2 and 2.5. So I can guess the critical temperature by just looking at my clusters. This is totally amazing, right? So this is such a simple example where you didn't need to know any physics. You ran the simplest clustering algorithm that exists, but you discovered a pretty sophisticated phase transition thing that happens, and you know that in one dimension it doesn't happen. Like it's exciting, right? And you don't need to know any Hamiltonian for this. You just need to know the clustering. So then you tell me, this is great. Now I solved the rest of my physics studies because I will just walk around the world and be like, yo, I am discovering new phases with PCA, right? So it's not so simple. Also, in your exercise notebook, you are going to have this ugly surprise, which is something called Icing Age Theory, which is also an icing model, but fun twist, it has a local constraints added. The Hamiltonian here is a sum over products of sigma z's on the plaquettes. Plaquette is this square that you see here. And there is a sort of dual mapping to this. Maybe you have heard about the Wilson loops, but if not, then not. Like, it's very easy to understand. Try to follow my mouse when I'm trying to connect the orange ones, and then try to follow this first line here. So I'm connecting the orange ones, connecting, and I reconstructed this first line down here. And then you can squint at this slide a little bit and see where the lines go. And it's very easy to check whether this plaquette condition has been met. Specifically, the plaquette condition is that if you get a lowest energy by having the even product on each plaquette. And if that's violated, like for example here, your loop breaks. And you see that in the second example, you have a lot of breakings. Of course, that if I know this, and I know that I should check the loops, or I should manually go and check if all the plaquettes meet the condition, then it's easy. But imagine I don't know this, and I am going to test you on this later on. Spotting a difference between this configuration and this configuration is actually kind of hard, right? And so what will happen when you run the PCA on that? You are going to get this ugly thing, and you don't learn anything about whether it has a phase transition or what does it have. So this is just one example that I took the icing model I showed you before. I add seemingly simple local constraint, and this is over. And fun fact is, I was actually struggling with this problem a lot at the beginning of my postdoc. You cannot find a clustering technique that separates these. You need to do something much smarter, which we are going to learn later in this course. So this is just a second example on which you can try to run your PCA. Now I showed you. Yeah, there is a question.
So you just said that there's no. Could you just go one slide back, please?
You are going to check me on the rigorousness of the statement, and I agree it wasn't very rigorous. Please go ahead.
I just like have one question for interest. Because does it get any better for like if you're trying to basically use the down the picture down at the bottom, you know, where you have like all these loops, and if you try to find like some representation of this, does the clustering get any better then?
Yes, it does. I didn't try the simple linear method on the loops. I think you would have to do something nonlinear, but I think the loops you can probably cluster. But when people give you this problem, they would probably accuse you of cheating because you are using that, you know, the loop representation. So the moment you transform into the loops, I am confident there exists some kernel method that could separate them. And actually, why not in your notebook you can experiment and try the PCA? I would be a bit skeptical on that, but maybe it gives a little bit. But yeah, that's a great question. Thanks.
Okay, thank you.
So I won't attack you about the rigorousness of your sentence, but do you do you have some intuition when clustering fails? Then some general idea.
Okay, so a simple thing I can say is that this is a classical model, right? Like it's complex, but it's still classical. And basically, to my knowledge, the moment you start doing this projective measurements on a quantum data, you have a problem, and you need to implement some kind of like more sophisticated techniques, because you kill your correlations every time you project, and then this kind of clustering thing is not going to resolve that. So I think like a quantum classical is like a really hard boundary, but then you see that you can come up with a classical models that also do not meet it. What I have to say here is that this is specifically tricky example because it doesn't have a phase transition in the same sense like the icing model I showed you before. It only has this like finite temperature crossover, because it's this kind of like you can think about it as like some kind of topological constraint has broken here. So yeah, I guess like the having some kind of topological local constraints lowers your chances significantly, but I am not aware of any like rigorous mathematical statement about where the boundary is for the classical model.
No, sure. Okay, but that was my guess, kind of. Maybe topological and global order parameters, this kind of stuff is
right. Yeah, exactly. Yeah.
Okay, thanks.
Great question. Okay, so just to quickly finish this part before I send you to the break. So I just showed you like a super basic thing. So if you are just starting learning about clustering, you will find that there is a huge zoo of different clustering techniques. So this picture I have on the background is just like a picture taken from a scikit-learn, which is also one of the tools that you will use in your exercise notebooks. But just to give you like hand-wavingly good places to start, so you don't get overwhelmed with all of these lists of different clustering and you don't know what they mean. A great thing is kernel PCA, which is similar to what we just did, but you can add a kernel function that can make it nonlinear. That basically does, you don't just do a linear separation between two clusters, but you can make it a little bit more interesting. And this is in principle quite powerful. And then one thing that is amazing is something called t-distributed stochastic neighborhood embedding, or t-SNE. Again, I never had to implement it by heart. There is an amazing package that you can download, and it's like a really powerful clustering techniques. And there is a lot of tutorials on the internet about how different hyperparameters there play a role. So if you are just looking into your use clustering on your data, if I were you, I would go PCA, kernel PCA, and t-SNE as the first three things to start and get you bit of the intuition. Speaking of t-SNE, I wanted to show you one thing that I'm really excited about. Now we are transferring a bit from the tutorial phase of my explanation to more of the science phase of the explanation, because I want to show you our recent exciting result. But so don't worry if you don't understand every word. Who has heard about quantum dots? Perfect. So you know that they are these quantum devices where you can isolate electron in all three spatial directions. One cool thing is that more recently people developed bilayer graphene quantum dot. Basically, using the fact that you can open a gap in a bilayer graphene by modulating the size of the gap, you can capture the electrons in this structure. Funnily, you may know that the graphene, especially the multi-layer ones, they are kind of mysterious theoretically. So our colleagues at ETH measured this plot of the conductance through the dot. So it's a energy as a function of magnetic, a conductance through the dot as a function of energy as a function of perpendicular magnetic field. And there was a lot of like there is not a good persuasive model that would fit this data very well. These two lines you see, those were the best fitting theoretical model at the time. So, you know, so we just we just did a super simple thing where we reduced the solution to the problem to the determinant problem. The pictures you see on the left, the density plot is the value of the determinant. And again, you have energy as a function of the magnetic field. And then the darkest line is the line where they would measure the state. That's the determinant 0. That's the eigenvalue. We created a bunch of these different determinants from the model for this data. And then we ran t-SNE on them. And this is nothing, just running t-SNE on this blurry determinants. And I get beautiful clusters that are clustered by the pairs of quantum numbers that describes these states. Sorry. So this is just like a quick flavor to give you that this is a really pressing problem. I have data that I cannot really explain. Then I built a simple model for it. I cluster it, and from which cluster my incoming data fall in, I can immediately predict which are the quantum numbers of that state. So that's kind of more higher level thing that what I just show you with the icing, but it's the same thing. You just take experimental data, you don't have a model, you run a simple algorithm, and from the structure of just looking at how does it look in the coordinates of this principal component, you actually see that there is some exciting physics going on. So that was just like a final cherry on top. Now I told you a lot of stuff, so let's take a 15. You have a question.
If you go back to the slide, teachers. Okay. There's in this t-SNE clustering, there's some blobs which have like additional structure. And you have the same color for those. So it looks like there's maybe even more structure than just the two quantum numbers. So for example, the gray one at the top, you have these two distinct groups even in the gray blob. Like, is there something you looked into? Or?
Yeah, this is a great question. So this data, so I could color it for you to show you a persuasive argument. They are from a numerically generated data. So I know what the quantum numbers are. So I colored it by the quantum numbers that my students used to simulate that. And basically, after we were looking at this for a while, what we understood is that you have sort of like you can think about it as like sort of like a lower probability configurations here. So when you are sort of creating Okay, so yeah, so just, can you hear me? Okay, so just to quickly finish this one. So basically, yeah, they are just like lower probability, but exactly like what you're saying. If I didn't know this, I might have thought they are a different data structure, and yeah, we should do a better sampling here before we publish it. Okay, do we have any more questions before the break? There is one.
Yes, so what do you learn from this analysis? So what are the principal axes here? And I mean, so you can cluster different phases based on the conductance, depending on the energy and magnetic field, but what do you learn of the system by classifying them like this?
Okay, so yeah, that's a great question. I skipped a lot here. Basically, the Hamiltonian of this system can be written in a way that is only depending on 4 numbers. 2 numbers are these U and V that you see here, which is a gapping and confining potential for the dot, and they are continuous numbers that you can just fit with some whatever complex algorithm that we haven't yet discussed. And then to characterize each state, you need 2 quantum numbers. One is the Valley number, in graphene, there is this valley splitting. And basically, if you have a state that goes up, it has a tau equal 1. And if it goes down, it has a tau equal -1. And then you need angular momentum. And when you know all of those 4 things, you describe all your states and your Hamiltonian. So basically what we did here is that by this simple clustering of determinant representation of the problem, we can, for the incoming determinant, without knowing any of those parameters, tell what are these 2 discrete numbers. So it doesn't solve the problem in its complexity, but it's kind of like a cute curiosity that I can get some data and immediately determine 50% of the parameters that actually describe the problem. I don't see any more raised hands. So let me go back to my meme and you guys take 15 minutes and think about clustering and icing models. And if anything comes up that you want to ask me not on camera, just come by and ask.
Now we will take a 15-minute break and we'll come back here in 15 minutes. It's not a coffee break. Coffee break it's at 11. So.
One. Okay. Yes. So I have a question about the PCA method because when I look on the data that you show, like the first thing that I saw is the oscillation of the conductance with the magnetic field. And my question is, are we losing any information after this new projection in this method? Because I do not see these oscillations on this data that you show now, but on the previous slide, it's quite clear to see. Yes, so on this slide, I see some oscillations of the peak conductance with the magnetic field. And on the next slide, it's quite hard to see. And I wonder if it's because of the losing of some information because of the projection or because of the different of the different plot, which is, let's say, not showing this kind of features, but it's pronouncing other.
Okay. So yeah, that's a great question. So somehow you need the magnetic field to see this splitting, basically. So it's like the whole state is implicitly written as a function of the magnetic field. If I wouldn't have it, I wouldn't know that this is tau equals -1 and tau equals to 1. So, but overall, right, this is a great observation that like data can be very structured. So maybe let me first answer this very generally, that the data can be very structured, and whenever you do this kind of low dimensional projection, you may lose something important. And then it's kind of a question of the interpretability. And I can see how this example without much more context is very confusing, right? So maybe thinking back about this simple icing model, right? Like you know enough about it from the interpretability point of view to look at it and be like, okay, that's a phase transition. And so if I would completely separate myself from any knowledge of this data and I would just be like, this is a data, then I could look at this t-SNE projection and I could think, okay, then there is however many, this is 9 different phases, right? And that would be completely dumb. So there has to be some knowledge that sort of goes into it, like from your information that you have about your data. But like generally, this is really true that if you are dealing with something completely unknown, just trying one clustering technique, seeing the clusters and then be done with it and walk away, that's not a good idea. You wanna, for example, if you open Scikit, you will have all of these tools and you probably want to run a bunch of them and see what they did. And if you will see a consistent clusters from a multiple clustering techniques, then you can say something. So I think this was actually like a really great question to kind of also say that this is data-driven method that showed something really fun and exciting on a simple example, but in practice you need to multiple test everything. And also a good idea is to pick a different subset of your data set to avoid having some kind of redundancy that is encoded in like how your data is organized and so on and so forth. So it's not always so straightforward. So multiple techniques always, and multiple restructuring of your data always. Do we have more questions? There is one.
Maybe regarding the background pictures on the previous slide, it seems like I have the same pictures but different kind of classification in terms of clusters. Is there kind of a parameter which can modify the meaning of a cluster when I run the algorithm?
Yes, absolutely. So this PCA we did, it didn't have any hyperparameter, so to speak. It was very do this, find the vector, then you see the clusters. But a lot of the sophisticated clustering algorithms you can tune. Sometimes the parameters are continuous and you can really shape and move around your clusters. And this is again related to the data structuring. It doesn't mean that there is something wrong with your how you generated the data. It's just that it's just the flexibility of the algorithm, and there is a part of finding the correct hyperparameter is a part of your, say, optimization problem. So for example, one thing that you could do, like a most basic thing, is that you could do, for example, a random search in your hyperparameter space or something like that. Or you can run like a second layer or more sophisticated optimization on your hyperparameter. But exactly as you say, like there is always something you can tune to reshape your clusters. Or not always, but in many cases. Thanks for the question. So, right, now we had some follow-up. So this will not be, so before the break, we saw two things. That on a very simple model that you learn to also solve exactly, you can run a simple clustering techniques and get amazing result. And then you also saw that on a little bit harder model, it doesn't work so well. So now we are going to take a next step to more, let's say, standard machine learning direction. And that will be a neural networks. And we will see if we can solve the same classification problems using neural networks. There are other classification and machine learning techniques, so I am deliberately choosing something here. Okay, who has heard about neural networks before? Everyone. And who has an experience of coding them? Also almost everyone. So the second half will be painless and quick. How should we do this? Then let us do this more interactively. So I'm not talking all the time. So you know that the neural networks are modeled on this analogy with the human brain, that you have interconnected neurons, except that our model is much more simple. This drawing here is taken from amazing lecture by 55D at Stanford. And it tells you what happens inside of a single neuron. Anyone would care to explain that for me and everyone else? If you have coded neural networks, probably you know what a single neuron does. Anybody knows? I am sure you do. I can wait. We have a raised hand over there, yellow t-shirt.
Yeah, so basically sticking to the picture that's shown from the left side, the axons from the previous neurons come in with some value x, and then like depending on the axon, then labeled x0, x1 and stuff. And then there's the parameters, the omegas, which which are tunable, trainable, which then all get multiplied with the x's and summed up, and then they reach the neuron, the cell body as it's called here, and you add the bias, which is another parameter which can be tuned. And to make sure the whole neural network is not just some linear combination, you need some nonlinear activation function, which you then apply to this summation, and then you get the axon, which then can be used by the next neuron, basically.
Perfect, thank you. Yeah, this was a great explanation. So there was this interesting point that you said about nonlinearity, right? If we want the neural networks to learn something interesting, to map inputs on outputs, you want them to be able to model arbitrary functions, right? So nonlinearity is really important. So this is a very simple model where in the first step, you just do your standard linear combination with some constant on top. So that's just a simple linear transformation that you know. And then after you did that, on top of that, you add some nonlinear so-called activation function, f. And then what you can do is to layer these neurons into the networks. And then it looks like this, where each layer has this final output function as a function of your data X. And then in the next layer, you compose the next function and so on. Exactly as you said, the W's and the B's, those are the weights and biases, the parameters of your linear transformation, and those are your chainable parameters. And for each layer, I can represent the weights as a matrices, right? The ij input of the matrix is a neuron I being connected to neuron J in the same layer, and so on. Now, about this activation function. So it would be kind of tricky to just have like super generic nonlinear function and then try to train that, right? So we kind of cheat our way out of it by doing a few parameter linear transformation and then putting a fixed nonlinear function on top. Here are just some standard examples of such nonlinear functions. So for example, ReLU is 0 until a constant and then linear. Then you have a sigmoid function, or you have a hyperbolic tangent that looks a bit like sigmoid, but with a little bit sharper edges. With exception of the last layer that I'm going to talk about later, my advice is that this doesn't matter super much which one you choose. Don't quote me on any computer science conferences, but for our physics purposes, for the simple models, especially that you have in your exercise notebooks, probably nothing is going to change if you exchange ReLU for hyperbolic tangent. But feel free to test that. I have yet to arrive at the example in physics where this would play a substantial role for me. So now, how do the weights look like? This is again a picture from the lectures by Fai, and what she shows there is a difference between badly chained network and well-chained network. So on the left, you have some weights that it just looks like a noise. It seems basically random, right? What shouldn't happen in your network is that you train it and then you plot the weights and there is no structure in it whatsoever, right? Some of you at the beginning pointed out this very important issue of interpretability when it comes to machine learning. It's this thing, right? If I want to solve a specific problem in physics and I choose a Hartree-Fock approximation as an ansatz and then I solve it, then I know exactly what each term means, but this approximation is also super specific. Now think about these neural networks. we are doing the same thing with spins, as you will see 2 slides later, and as you just told me, many of you already know, that you would do with dogs and cats when you classify them on the internet. Like, just think about how general such a method has to be. So then the interpreting what it actually does has historically been an issue, and I will see if I have time to get a little bit into that later. But like, so I cannot, just looking at this weights, I think this is from one of these huge image nets with a big convolutional kernels. I don't tell you that this square like shows me something super meaningful, but at least I can print my weights and look at if there is some structure in them. I will show you another indicators later on, but it shouldn't be that you are training a monster network with 2 million parameters. You train it for 6 hours, then you print the weights and you get some noisy nonsense, because then it's basically predicting a random things on your inputs and is going to fool you. So this is just one of the things to say, that when we are talking about interpretability, it's a still big black boxish, but this is a simple thing. As I just told you, the weights, they are just matrices. So why don't look at them? Now, there is the question of chaining. You also told me at the beginning that you understand very well that the difference between AI/machine learning algorithms and like standard algorithmic techniques is that the machine learning algorithms learn from data. So we set up our model now, and now we said that the W's and B's are the chainable parameters. So now we want to chain it. So roughly speaking, how do you train it is this. First of all, you define a loss function that you will minimize during training. Who knows some examples of loss functions? I see who haven't spoken recently. Yeah, please go ahead.
Sorry. So for example, for regression, you usually use the mean squared error.
Any more examples? I'm looking for a discrete example specifically. You had non-discrete, but go ahead.
Some KL divergence, so some probability distribution.
Like a Kublak library. Yeah, that's a great example. Anyone has one more?
The log likelihood, which is the same as the Kuplan-Leibniz.
Right, that's good. I need a discrete one because I'm going to explain you how it works on a discrete loss function. You all know the regression stuff. Anyone knows a discrete loss function? We have one person here. Oh, sorry.
Categorical cross entropy, which
Perfect.
is more or less scale divergence.
That's also very true, but I wanted to hear the cross entropy. I guess you wanted to say the same. Perfect. Right. So you already know how the loss functions work, but like either way, so you can imagine whatever it would be, but treating it as a generic function A, you calculate the derivative of your loss function with respect to your weights and biases and update them like so. Now there is this epsilon hidden here, and that's something called learning rate. So if you have a complex optimization landscape, you can think about it, it like has valleys and bumps. The learning rate gives you the scale on which you want to adjust this rate of change. Imagine I have a valley that are on profiles where the local minimas are on this scale, but I will make jumps in my gradient that is this big. I will never recognize any of the fine structure that I am trying to optimize. So this is what this parameter tells you. It tells you how you minimize your adjustment steps of your weight with respect to your gradient landscape. And in a lot of these benchmark test problems on the internet, you will get standard learning rate 10 to the -2 or 10 to the -3, and it's just going to work. When you start testing on a physics data, oftentimes because the optimization problems we are solving, the the ground state energy we are trying to find of a complex models is very subtle because the local minimas are not super well pronounced. You are gonna have to go way down with the learning rate. Again, you will learn in your exercise notebook that this is just a parameter you can adjust with something. Typically, it's called LR. That is just a parameter of your optimizer, but sometimes it's hidden and you need to look it up. So if your network doesn't do what you want, looking at the learning rate, again, quick fix, just like giving you random advice, like with the weights, this is one thing that you want to be aware of. So now the question is, how do we calculate this derivative, right? Because what is the derivative of the loss function with respect to some random weight? So you remember a chain rule from your calculus classes. If I want to differentiate a function f that is a composition of two functions g and h with respect to the variable x, I am going to calculate it as in differentiating the inner function with respect to x and differentiating the outer function with respect to the inner function and multiplying them. Chain rule, right? Like just not that this is standard for you. So this is then applied to a neural net. By the way, I am going a little bit faster than I would normally here because so many of you said that you have already coded this and seen this in the past. So I don't want to bore you, but like tell me to slow down if needed. So okay, so I want to calculate the chain rule for the neural network. How I am going to do that? I want to calculate, so the output is the last layer. So here I have an example of 3-layer network. So the output of the last layer is this thing, and I want to calculate the loss function, the derivative of the loss function with respect to the weights. So you start by using the output of the network and you calculate the derivative of the loss function with respect to that and evaluate that. Then you go one layer back, you calculate the derivative of the f2 with respect to the f1, and then you go all the way up front where you calculate the derivative of the f1 with respect to the weight, and so on and so forth. So you can sort of decompose all the derivatives of your loss function that you need to update the weights into such a chain rule. This was a very rough presentation of a backpropagation algorithm. And this is something that you don't have to think about very much when you are using any kind of machine learning package, because they just implement this for you. But if you want for fun, you can later try to just do this by yourself, because you really just need to apply the chain rule. But using Keras or TensorFlow on PyTorch, you just say whatever .train and you don't think about it. But what the neural network does, how it adjusts the weights, is this backpropagation algorithm. Specifically, you calculate the forward propagation, and then during the backward phase, you estimate the error in the final layer, then propagate the error to the previous layer, then you evaluate all the derivatives. Now I am saying it as just this two-step process because I had only 2 hidden layers. If I would have n, I would just repeat this n times. Then you combine all these partial gradients into the final gradient using a chain rule. And then you update the weights using the gradients that you calculated. Okay, so this was kind of technical. So let's look at like a super concrete example of how this works with a super concrete wave function and super concrete loss function and super concrete chaining examples. So I picked here 2 movie franchises, and I want to build a neural network that gets a character from a different movie franchise and predicts whether is a Star Wars or Star Trek. So with classification, which is something that we will do later on physics data. So actually, let me emphasize one thing really here, is that this is the task of classification, and that's why I was grilling you for giving me those discrete loss function, because this is a very simple task. I don't want to extrapolate how would the different Star Trek character look like. I merely want to get a picture and decide, is it a class A or is it a class B? And that's the only thing that you wanna do, right? So this is a typical classification problem, and there is a lot of benchmark problems on the internet for this. For example, an MNIST, where you can build a simple neural network to classify handwritten digits, but we will do something more physics related. So for the classification, there are two very important things. The last layer activation function. So when your neural network has an output, neurons, and you are deciding between multiple classes, the output neurons in your last layer give you a probability distribution over these classes. So now we have two classes we want to classify. So my output will be two neurons, and one neuron will tell me probability, this is a Star Trek character, and other neuron will tell me a probability, this is a Star Wars character. But if I want it to be a probability and not just some random number that is like -60 and I don't know what it is, I need to renormalize the output and actually map it on a probability distribution. A handy way to do that is to use this activation function in your last layer. It's unsimilar to other activation functions you have seen, but there is this normalization that allows you to map it on the probability distribution. And then your loss function is very simple, which is this categorical cross entropy that you mentioned. And it's just a cross entropy between correct distribution and predicted distribution on these final layer neurons. So let's look at the super concrete example. So let's look at it as just a classification on two samples. My label, my probability distribution that is the correct one, will be 1, 0 for Leia, that's class A, and 0, 1 for Spock, that's class B. And then the network is going to output vector that has two components. Both of them will be between 0 and 1, and they will tell me a probability, it's a Leia or it's a Spock. And then if I translate this into a loss, I will see that the loss is the smallest when it's correct. Actually, now I will give you 30 seconds to look at this and try to actually understand the vector, right? Right, and you see that when I am here, I will get this prefactor when I am in the correct class, and when I get that here, I get the other prefactor when I am in the correct class. And that's really how it works. And closer to the corrector class I am, the lower number I am going to get. And that's really how it works. So now I gave you this like image classification example, which is the one that you have seen many, many times. You can do it with handwritten digits, dogs and cats, whatever. We looked at this simple categorical cross entropy for Leia and Spock. So now this is a question that Roger Melko and Juan Carrasquilla, who is also one of your lecturers this week, asked themselves in 2017. Can we just take the physics data exactly as they are and classify them the same way you would classify these fun sci-fi images? So going back to physics, let's go back to our beloved, well-studied Ising model. And let's say that Leia is, of course, ferromagnetic and Spock will be paramagnetic, right? So it's again just the two categories. And then in your notebook too, you will again load this Monte Carlo generated data. You will have the pleasure of creating the labels for yourselves. Basically, your PCA told you approximately where the phase transition is. So what you are going to do that for the data that are enough below of your guess guest phase transition or guest from the PCA, you are going to label them class A. And the data that are a bit higher, you are going to label them class B. And then you are going to build feed-forward neural network the same way I just described to you they are built, and see if you can classify phase A versus phase B classification task only from the data alone. Okay, now let's do a human classification challenge. So anyone dares to tell me which of these images are which phase?
A and D are symmetric phase, while B and C are in the broken phase.
Perfect. You see that, and there was I could have find the trickier examples, but I wanted to find the pedagogical one. So it's exactly how you see, right? It's not super tricky to decide like which of these samples are going to have a temperature which is bigger than the critical temperature, and which samples are going to have lower. So this is a task that the human can do really easily. We had one person answering, but I am sure that all of you were thinking the same, right? This is not super hard. So then it shouldn't be hard for a few neural network to do the same. So what are you going to do in your exercise is this. You just build a feed-forward dense neural network with a single hidden layer. Here I took a printout from Keras. You will see that in the notebook, but feel free to experiment with your architecture. Like we did for the PCA, the simplest thing you can do is just to flatten everything. So instead of, we will learn later about how the two-dimensional looks like, but now we just have neurons, 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 and each neuron is one data point, right? So I need to take my two-dimensional input and flatten it into the vector. So I have a 900 neurons in the first layer. Then you will have one hidden layer, and then you will have two outputs in the output layer, just like I just explained to you. You need a classification between two between two options. So you need two neurons. Now, the hidden layer, I put here 32 because I don't know, it was random. I am going to ask you to experiment with this number a bunch and try to find out if you can come up with the minimal example that still does the classification well. And you can sort of get a feeling how much the accuracy of your models actually depend on varying the number of neurons in the hidden layer. And the loss function you are going to use for this is, of course, the categorical cross entropy, because we are just doing a binary classification between two phases. Then you are going to do again something amazing. Like before, you were going to plot a plot from the Lei Wang's paper from 2016. In this part, you are going to plot a picture from the Karaskia and Melko paper from 2017. What is in this plot is the probability in the output of the output neurons. Blue is one, red is the other, as a function of your temperature divided by J, but for us that's one. And what you see here, that this one is really sure, really sure, but then it starts decreasing and then it goes to 0. And the other one is doing exact opposite. And the additional benefit of plotting it like this is that you can check where they cross and how well that corresponds to the analytical calculated critical temperature. And now again, you want to play with the number of neurons in the hidden layer, with your learning rate, with your hyperparameter, to figure out what it is that gives you a best intersection. Actually, the best thing to do it is what Roger and Juan did here, where they did the same tasks for multiple system sizes, so they would really see that crossing clear as day. You only have a L30, so you can only cross 2, but you should be still seeing beautiful agreement with the theory. right? So again, let me repeat this crucial message. Before it was clustering, now it's a neural networks, but it's the same thing. You get a data and only from the data, you learn something about physics of your system. In this specific case, by just looking at the probability distribution in the output layer as a function of temperature, you can discover where the phase transition is again. Okay, now I am going back to this Icing Age Theory with the local constraint. So let me repeat how this worked. This Hamiltonian is a sum over plaquettes where the plaquettes have their sigma z +1, -1 calculated as a product. So this plaquette would have a +1. This plaquette would have a +1 and so on. Before we were trying the PCA and it wasn't so nice. So let's try to understand intuitively why this is harder. Can you look at these and tell me which one is which? It's a little bit blurry indeed. Do we have any takers for this one? I explained you the rule. I am sure that someone can guess, right? I mean, after all, even if you just guess, it's a 50-50, so that's not so bad odds. So there is someone there.
Yeah, the B is the one that has the even number of dots, so the +1s, and the left has +-1s.
Perfect. Excellent. So when I plot it in this dual representation, you see it immediately and it's not so hard, right? But when I ask you just looking at this picture and you know the rule, it's a little bit annoying to distinguish. So imagine how hard it is to distinguish if you don't know the rule. If I would have really wanted to trick you, I would have told you nothing about the Hamiltonian. I would show you the screenshot and let you figure out for half an hour if you can figure out the rule, right? And that would be really, really tricky because you have so many options of what the local constraint should be. And now, if you don't want the neural network to cheat, you cannot tell it the rule, right? Because that means that you know the Hamiltonian. So this was an experiment to tell you that while with the Icing model, you look at it once and you know immediately. With Icing Age Theory, it's not so straightforward for you to just see. So maybe there is some merit to do something algorithmic. So here I just copied pretty much the same model. The input size is slightly different because of the different lattice size. The dense layer is a little bit bigger, but you will get to experiment with this in your lecture notebook. But before you spend 3 hours on that, a spoiler, this will never work. But go ahead and test your hyperparameters. To make this work, we need to not flatten the thing that actually gives us the local constraint, and we need to build a neural network model that actually is able to capture what the local constraint is. And for this, we need something called convolutions. I am sure you also have heard about those. Hands up, who did? Great. Anyone can tell me what they are specifically good for? I see a hand all the way up there.
So when you have like structured data, so typically images where pixels have spatial relationships with the pixels next to each other, then it's really good.
Perfect. What a perfect explanations, right? Because for us, the pixels that have a spatial relation with the ones next to each other are the spins that have a very specific constraint. And that's why going convolutional is the thing to do here. How this works is that you train the so-called filter or a kernel that is relatively small and scans through all of your data. So here is just like an example here, but let me show you really in detail how it works. If we would take the kernel size 3 times 3, so in the two-dimensional data, it's going to look like this. And then you do discrete version of the convolution. Basically, you do a pairwise sum, and then you sum everything up. And if we go over the pairwise sum here, we will see that the two dark ones meet, and we will get a visually very dark one on the output. Then something called stride tells me how much I shift this window when I'm moving through the data. So this is stride 2. And then I could repeat this, and I get that one, and so forth and so on. I just did like a quick scan, but you would just go systematically with your window through everything. So you are connecting you are not connecting like before all the neurons in one layer to all the neurons to the next layer. You are only connecting to the kernel, and the kernel is the same for the whole data, but you keep shifting it to understand these spatial relationships. And usually what you do is that you actually pick a multiple kernels, and ideally each of them is going to pick up a different spatial relationship. This is just like an example from Keras to say that, again, you actually don't have to think too hard about what a discrete convolution is, because all that you have to do is Keras tf.layers convolution. And you put number of filters, kernel size, stride, input shape, and activation. You just put it into your layer and you are all done. There is one thing that I keep a bit like sliding over because I want to move over to physics from this technical stuff, but that's a padding. I introduced you here an example where the kernel sliding through the data fitted exactly to the dimension of your data. In the reality, it may be that the kernel size you need to recognize and identify the spatial relationship that you want is not the same that's the exact multiplicator of your data structure. So you need to introduce padding. If I just have a Spock and Leia, I am just going to pad it with 0 or black pixels or white pixels, and I'm not going to care because it's not going to mess up the classification of the fact that there is a Spock holding a cat in the middle of the picture. But in physics, we care about boundary conditions. Specifically with all of these things, you also notice that there was a periodic boundary condition in play. So what you need to implement is something called periodic padding, where it's basically a periodic boundary condition on your data. To save you any annoyance, I wrote a function for you that does this in your notebook, but be aware that this exists. But in the end, it's nothing too complex. It's just about making the dimensions of your matrices fit when you are doing the training, right? So when they don't, it's likely that your input and your stride and filter, the objects that created some dimensions doesn't fit, and then a padding is a good way to solve that. Another thing I want to tell you about before we finish is regularization. We keep talking about building a models that, like a human brain, only learn from data. So imagine that you learn to classify what each fruit is as a human. And then I didn't have an avocado or seen one until I was 20 something. And then I found I'm allergic to avocado. But nonetheless, I wouldn't know how to classify an avocado if I didn't see example of how avocado looks like before. And this is something called overfitting, that you built a model that is not general enough to generalize from your training sample to the new data, but it just reproduces something some fixed features that it learned on a training samples. A super simple way to prevent this is something called a dropout layer, where you basically kill connections to specific percentage of your neurons. So this would be a command. Again, this is in Keras, but TensorFlow is the same, PyTorch is almost the same, with the argument that tells you that 30% of your weights should be killed. You do this, and in each backpropagation, you just randomly select 30% of weights and don't adapt them. And this is a great way to stop making over 50 iterations, picking up on a super specific feature that would then tell you that if it's in a category fruit, it has to be red, round, and look like an apple. Like, you want to generalize further from that. And this is just like a really simple numerical thing on how to do that. There are other regularization techniques. We don't have to worry about them in this exercise. Everything you need to do in your notebooks, you can just do with dropout layer, and you will need a dropout layer for the IGT classification problem. But there are other ways to regularize. This is just the terms that you can add to your loss function. Is L1 and or L2 regularization terms that basically you add the values of your weights with some prefactor. This forces the loss function, this forces the model not to put a single weight, 1 million, and all of them to 0. It forces it because if you want to minimize the sum, you want to have the values of the weight systematically distributed. So this is just something that I showed you once, but all you need is going to be this dropout. So now you are going to solve this Icing Age theory. And now I told you about the convolutional network and dropout layers, and those are the ones that you are going to make it work. I am putting here example with like 2 dense layers, but again, you can experiment. These architectures are typically usually very flexible. Fun fact, in the paper of Karaskia and Melko, they got super high classification precision. It went from just dense network, just like throwing a dice, to like over 99% accuracy, because you find a convolutional filter that learns your gauge constraint, and it learns that the label A is connected with, you should look at this product of the spins and it should be even. Like, it literally learns that, but you can only learn that if you have this 2-dimensional structure where the data are presented to you in their actual spatial relation, and you have a model that you can train that extracts this spatial relation from your data. So this is something that you are going to do in the second half of notebook 2, and then you can learn to do convolutions and dropouts. And I think with that, I'm already 1 minute over time. So let's stop here, and I will be back in the afternoon for 2 more hours of this.